Three footnotes to our discussion of motional EMF. I want to emphasize that this electric field here is not an induced electric field. This does not come from electromagnetic induction. This is a traditional, let's say, electric field that's generated by positive charges and negative charges. And so the field line begins here and ends there, has nothing to do with Faraday's law. Footnote number 2, regarding this equation. We have recently written down a modified version of this that takes into account the possibility of a time-dependent magnetic field. Going back to a previous video, okay, when we were discussing Faraday's law, we said that this equation here, our potential field relationship along some open path, might need to be modified if there is a time-dependent magnetic field in the background. We might need to add some Faraday term. We never specified what that term was for an open path. But here we are using just our original version of this equation without some additional Faraday term. So did I mistakenly ignore this term when I wrote this down? The answer is no. What we did was fine, because this additional term depends on a time-dependent magnetic field, a magnetic field that's changing with time. And in our scenario, we had a uniform background magnetic field. So as the bar moved through that magnetic field, since the magnetic field was the same at all locations, the B field that the bar experienced was the same at all locations. There was no time dependence to that B field, so no need to add a time-dependent B field term to this equation. No need for this. So this equation as it is still fine for us to use whenever we have a uniform magnetic field or a constant magnetic field. This is fine. It's only when B is changing with time that we need to worry about induction type effects. Okay, that was footnote number 2. Now footnote number 3, I just want to remind you of a similar phenomenon we discussed earlier called the Hall effect, and suggest that you look back at your notes on the Hall effect to distinguish it from this. So, quick look back at Hall effect as a reminder. That was when you have some wire here with a current running through it in the presence of some external magnetic field, and because of that current being driven by a power supply somewhere, we get a polarization across the wire in the direction perpendicular to the direction of the flow of current. So we have a polarized wire because of the current being driven through in the presence of this magnetic field. That's different. That's the Hall effect. That's different from what we've got here. This polarization is not due to a current being driven by any power supply. This polarization is due to the conductor itself physically moving through the magnetic field. So having pushed the bar through the magnetic field to the right, we get a polarization in the bar in the direction perpendicular to the velocity. Okay, so that's two different effects that can polarize a conductor in the presence of an external magnetic field. The Hall effect versus this motional EMF.